Welcome back. Today we're going to be talking about the basics of hypothesis testing. Methods of inferential statistics use sample data to make an inference or conclusion about a population. The two main activities of inferential statistics are using sample data to estimate a population parameter. Remember, when we say parameter, we mean things like mean or standard deviation or proportion, such as estimating a population parameter with a confidence interval. So that was the first way that we did it. Now we're going to be talking about how we test a claim or hypotheses or a hypothesis, let's say, about a population parameter. So in statistics, a hypothesis is a claim or statement about a property of a population. A hypothesis test is a standard procedure for testing a claim about a property of a population. So if I say something about the mean of a population or the standard deviation of a population or what percentage of a population, the main objective in this chapter is to develop the ability to conduct these tests for the mean, the population proportion, p, mu, and a standard deviation, sigma. Let's go about over the little parts of all the hypothesis testing. The null hypothesis, which is denoted by H sub 0. Now, I'm never going to call it H sub 0. Let's write our note here. This is pronounced H naught, which is N-A-U-G-H-T, but it's really pronounced H naught. So the null hypothesis H naught is a statement that the value of a population parameter, such as proportion, mean, or standard deviation, is equal to be some claimed value. We test the null directly, either reject the null or fail to reject the null. The alternative, denoted by H1, HA, or H capital A, our book uses H1, but you may see any of these as the alternative, is a statement that the parameter has a value that somehow differs from the null hypothesis. The symbolic form is going to have less than, greater than, or not equal to. So equality is always going to be in the H naught. If you're conducting a study and want to use the hypothesis test to support your claim must be worded so that it becomes the alternative. So usually the claim will be the alternative. Very rarely will we see the claim in the null, but more often than not, we should try to make sure that the claim is in the alternative. Let's identify the null and alternative hypotheses given some statements. Number 1, examine the given statement, then express the null hypothesis and the alternative hypothesis in symbolic form. Part A, the proportion of people aged 18 to 25 who currently use illicit drugs is assumed to be equal to 0.2. So since it says is equal to, that's got to be in our null. So here's my null and my alternative. Notice that I'm putting colons here, not equals, because I'm listing out these, so make sure that these are colons and not equal signs. The proportion, so that means I'm using P, because that's the symbol for the population. And because P is equal to 0.2, this has got to be in my null. So this is going to be P equal to 0.2. And because this is here, if this is equality, this one's got to be inequality, so P is not equal to 0.2. These two numbers should always be the same. This one should always have equality, and then this one has non-equality if it had mentioned equality, or it's going to have something like a greater than or less than if it's signifying that. Let's try another one. We want to claim that the majority of college students have credit cards. So if I say majority, that means more than half. So I'm going to say more than 0.5 to kind of remind myself that that's here. So my null, colon, hypothesis, and again, majority, so we're saying proportion. So we're assuming that this is talking about P again, because we're talking about proportions. And it's greater than 0.5. Should that go in my null or my alternative? That should go in my alternative because it's non-equality, P is greater than 0.5. This is always going to have equality, so whatever it says, I know that this is going to be equality. The critical region or rejection region is the set of all values of the test statistic that causes us to reject the null hypotheses. And I'm throwing this word test statistic here, so we'll talk about that a little bit later as well. The significance level denoted by alpha is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. Common choices for alpha are 0.05, 0.01, and 0.10. This is the same alpha that you would see in a confidence interval. When we said 95% confident, we said alpha was 0.05, and that's the same here. A critical value is any value that separates the critical region where we reject the null hypothesis from the critical values of the test statistic that do not lead to the rejection of the null hypothesis. The critical values depend on the nature of the null hypothesis, the sampling distribution that applies, and the significance level alpha. So that was a lot of definitions. Let's see if we can clear up a little bit of what that means. So this critical value here, let's say I'm talking about a null and an alternative. And let's say that the alternative is a greater than. I'm not putting any numbers here. I just want to give the idea of what's happening here. So greater than means that I'm a right tail. So I'm over here. The critical value, whatever this is linked to the critical region here. And so let's say that I wanted to be 95% confident, or I tell you that the alpha is 0.05, which is what we default to. If I don't tell you one, let's always default to alpha equals 0.05. That means that this region here is 0.05. This area is 0.05, and that's my critical region. The CV, the critical value, goes along with that either using inverse norm or inverse t, depending on what type of distribution that we have. If I do my sample and I get a test statistic somewhere in here, or I shouldn't say here, I should say here, so because it's on here. So let's say my test statistic. So let's say I get a critical value of 2, and I'm just making up these numbers, and I get a test statistic of 3, and this is 0 here. See how it's in my critical region? That means that's really weird that I got a 3, and so I would reject because I'm in the critical region. Let's say I got a test statistic of 1. Then it's not in the critical region. It's before the critical value of 2, which is 1, which is back here. It's not going to be rejected. So I would fail to reject here. This goes along with what's important for us too is the p-value. The p-value is the probability of getting a value of the test statistic that is at least as extreme as one of the one represented in the sample data, assuming that the null hypothesis is true. So let's go back to our thing here. If this critical value was 3 and I got a test statistic of 4, we said we were going to reject. Now this area here was 0.05, which means that there's a 5% chance that my test statistic is as extreme as 3 when assuming that the null hypothesis is true. My 4, if I say here, this area that I'm taking up here, should that be more than 0.05 or less than 0.05? It should be less than 0.05 because if this whole area is 0.05, then this would be less than it. So whatever this area is, it's got to be less than the 5%. And that's making us say that it's less chance. So it's a very small chance that I got a 4, assuming that the null hypothesis is true. So these figures kind of depict what would happen. It's kind of like this last one we were looking at. I had said this was a greater than, so that was here. If my sign used in the alternative is a less than, it means I'm a left tail, and so my critical region is over here. If it's in the right one, my critical region is over here, and I should have a greater than in my alternative. And if it's a not equal to, I should be somewhere in the middle, or I should have both sides, and I have two rejection areas. So whether it's low or high, it could be rejected. The null hypothesis is rejected if the p-value is very small. Now, this depends on alpha. So if it's less than alpha, then the p is low. And if it's bigger than alpha, the p is high. Now, if it's very small, the lowest alpha we would have is 0.01. So if it's very small, like less than 0.01, then it's definitely a rejection. But other than that, it depends on whatever alpha we choose, and our default is 0.05. This memory tool is useful for interpreting the p-value. If the p is low, the null must go. If the p is high, the null will fly. This is really helpful to kind of say to yourself as you're doing hypothesis tests, and you'll see us kind of write that down and talk through that as we do some testing. So let's talk about this though. If the p is low, then my p-value is less than my alpha. It's low. The null must go, which means that I reject the null. If the p is high, that means that my p-value is greater than alpha, and I should say probably less than or equal to alpha here. P-value is greater than alpha, then the null will fly, which means I fail to reject. So as we do them, you'll start to kind of just hopefully p is low, the null must go. It's low, I must reject the null. And once we do some, it'll make sense. But this is helpful to kind of keep that whole kind of concept in line. One big thing is not to confuse a p-value, and p-value could be capital or lowercase for this p-value. I tend to capitalize it because I don't want you to confuse it with the just p, with the proportion p. And this is for the population proportion p. So don't confuse the two, and that's why I usually try to capitalize it, but it could be p-value like this. And I always make sure I write p-value if we're trying to signify that to kind of keep them separate. So we have three methods that we can do. P-value method, which is the method that we're pretty much going to be doing. If the p is low, the null must go. If the p is high, the null will fly, and that's written kind of out here. Traditional method is if the test statistic falls within the critical region. That was when we were talking about the bell curve and we were saying where was it, do we reject it or not. That's definitely a way to do it. The p-value methods using the technology a little bit more simply, but we may talk about traditional method as well in class so that we can see how we can see picture-wise what's going on. Another option, instead of just using 0.05, so this isn't another option for a testing method, it's just if you don't have an alpha, you can leave that decision up to the reader if you want to reject or not. So that's kind of dependent on what you're testing on, the significance of it. Do I want a really low p-value or does it not really, how strong do I want my argument to be? You're given a test statistic in a right-tailed test is z equals 2.13. Find the corresponding p-value and denote it on the graph below. So it's a right-tailed test, which means I got to be over here somewhere. My z is 2.13. So this is the test statistic. I don't have a critical value, so this is my test statistic here, which is 2.13. This area is my p-value. So remember, area is a probability, p-value is a probability, and that area is that p-value, which is a probability. So this is my test statistic. We'll say TS for test statistic. So we've done area like this before, and the way we find it is going to be normal CDF. LUMS, lower is going to be 2.13. Upper is 1E99. Remember, that means that it's 1 with 99 zeros over it. So that's 1000, right, until there's 99 of them. So it's a very large number. And for these, my standard deviation is always going to be 0 and 1 since I'm in the standard normal distribution. And we're going to go to our calculators to figure this out. We've done this before, but let's go ahead and go to our calculators. On our calculators, to get to normal CDF, we're going second, VARS. Behind it is distribution, so we're in distribution now. I'm going to normal CDF and lower upper, so 2.13. My upper is 1 times 10 to the negative, or times 10 to the 99, comma 0, comma 1. Some of you, remember, may have it saying lower, upper, mean, standard deviation. So if you have that, just plug it in. Make sure you're getting this number. Usually we round off these to 4 decimal places, mainly because the tables do that, but and 4 decimal places is safe, so I would do 4 decimal places. So we're going to say 0, 1, 6, and that's going to round up to 6. Let's go back to our notes and finish up that problem. Okay, so we're doing back here, so we had gotten 0.01659 or 0.0166. So this is this region, which means that the probability that we get 2.13 or higher is 0.0166. And this is my p-value here. Depending on what my alpha is, if my alpha was 0.05, this is low and I would have rejected the null. But if my p-value, if my alpha was 0.01, this is bigger than 0.01, so it actually failed to reject. Let's try another one. You're given that the test statistic in a two-tailed test is z equals 3.14. Find the corresponding p-value and denote it on the graph below. So since this is a two-tailed test, it's actually going to be going 2 places, left and right. The positive 3.14 is going to be over here. Now I still need this area. So again, we're going to do normal CDF, LUMS, so my lower 3.14, my upper 1E99, 0, 1. Go ahead and do that on your calculator. You should be getting this. Now, a lot of students will say, oh, that's high because I got an 8. But that's weird because what should the whole thing be? The whole thing should add up to 1. So the fact that I got something big shouldn't make sense to us. And the reason for that is that's E negative 4. That means it's times 10 to the negative 4, which means this is actually 0.0008448. And now looking at it like this, we can see that that's very small. So this area right here is this amount right here. But it's a two-tail, so I have to take into account the other side. So I'm going to have to multiply it by 2 for the 2 tails that I have. And if I round off, you should be getting 0.0017, which under any account of what we've done, that's very low because that's less than 0.01. So we would reject the null for this one. We're talking a lot about rejecting the null or failed to rejecting, and we're kind of not tying everything together. And so this section might be a little confusing because we're trying to do all the little parts. But when we put them all together, hopefully it'll all make sense. And maybe you might want to rewatch this this video just to kind of see all the little parts on its own again to make more sense of it. Let's now talk about writing conclusions. Notice that we never support the null. We failed to reject the null. So when we want to say equality, we don't support equality. We say there's not enough evidence to reject equality. It's a little weird. Let's go ahead and try some using the same claim or the same type of claim, and then we'll start seeing what the differences are. So we're investigating the following, write conclusions based on the results. The claim was the proportion of Americans who prefer blue M&Ms is not 0.5. So if I say not 0.5, we should be able to come up, this is what we'd done earlier, we should be able to come up with these two. So here's the claim right here, is that it's not 0.5, and so of course my null must be equality here. The conclusion we got, so we got a low p-value, we rejected the null, and so I'm rejecting this. If you decide to cross out the way that I do here, make sure you can still see, and that I can still see on a test question, that what you had written. Or you can just write reject next to it, you don't have to cross it out. So if I reject the null, I can support the claim. So I am saying that the proportion is not 0.5. Now we have to say it in certain ways. Let's go ahead and write a statement here. There is sufficient evidence to support the claim that the true proportion of all Americans who prefer blue M&Ms is not equal to 0.5. So let's look at a couple things here. You should always say there is sufficient evidence or there is not sufficient evidence. Or you can say enough. There is enough evidence or there's not enough evidence to support the claim that the true proportion, you should say the true proportion because we're doing a sample, we're making an inference on the whole population of all Americans. This is addressing your population, depending on what the population is. If they don't give you a population, you could say the true proportion of the population if they're being vague about what the population is. Who prefer blue M&Ms is not equal to 0.5. So then I'm addressing the actual claim, and I'm addressing it in terms of what the question was asking for. Let's try another one. So I have the same thing. The proportion of Americans who prefer blue M&Ms is not 0.5. So I have the not 0.5 here, the equality here. This time when I ran my test, I got a fail to reject the null. So I can't cross this out. I failed to reject. But remember, we never talk about the null. I always have to talk about the alternative. So if I fail to reject, I don't say that it is 0.5. I say there's not enough evidence to say that it's not 0.5. So we're going to say there is not enough evidence. There is not sufficient evidence to support the claim that the true proportion of all Americans who prefer blue M&Ms is not 0.5. Now, we're doing a lot of writing, so make sure you kind of read it through again and make sure it makes sense as a whole statement, because by the time you finish writing your conclusion statement, maybe you're like not tying it in. So we had said that it was failed to reject, so I can't say this, so I can't support this. So there's not enough evidence to support the claim that the true proportion of all Americans who prefer blue M&Ms is not 0.5. Let's do the same one, greater than 0.5, and this time I said greater than 0.5, reject the null. So now I'm rejecting the null here. Can I support the alternative? Yes, we can. So now we're going to say there is enough evidence, there is sufficient evidence to support the claim. And then I'm talking about the population. My population was Americans. Support the claim that the true proportion of all Americans, because I'm talking about the whole population, who prefer blue M&Ms is greater than 0.5. So there is sufficient evidence to say that the true proportion of all Americans who prefer blue M&Ms is greater than 0.5. Let's do the reverse of that. So I have the same thing that I'm saying that the claim is that it's greater than 0.5. So here's my null and my alternative again. This time I failed to reject, so I can't cross this out. Can I support that it's greater than 0.5? I can't. So I can't support this. So I don't say that I support the null, because we never talk about the null. I say there's not enough evidence for me to say this, so I can't support this. So we're going to say there is not sufficient evidence to support the claim that the true proportion of all Americans who prefer blue M&Ms is greater than 0.5. So there's not enough evidence to support the claim that it's greater than 0.5. So kind of, again, look it over just one more time. You have all the pieces in there about the population, the true proportion, or the true mean, or whatever we're doing. There's not enough evidence, but kind of look it over and make sure that it makes sense of what you're saying. Don't just follow a formula of what I'm writing. Make sure you understand what the conclusion, what you're actually saying for your statement. Now, this isn't to say that the proportion is not this. It's just that I don't have enough evidence to say that it is greater than 0.5. And this brings us to errors, and we're going to talk about that next. So a type 1 error is the mistake of rejecting the null when it's actually true. The symbol alpha is used to represent the probability of a type 1 error. The type 2 error is the mistake of failing to reject when it's actually true, actually false. The symbol beta is used to represent the probability of a type 2 error. Now, this is a little confusing. Let's go ahead and do one. So let's say that the null, I assume that the dog doesn't bite. So that's my null, my null. And then my alternative is that the dog does bite. Write a conclusion that would result from a type 1 error. So if I have a type 1 error, that means that I rejected the null when I shouldn't have. And then I'm going to be doing a type 2 error is when I reject, or I fail to reject, when shouldn't. Now, here's the way that I like to kind of think of it. And don't do this on your paper. I want you to, because I can't put my finger on it, but go ahead. If I say type 1, then put your finger above this. So for type 1, don't do what I'm doing, but put your finger so you're blocking this. And you're assuming for type 1, you said the dog bites. But you shouldn't have, because what you covered was actually true. The dog doesn't bite. Type 2, so 1, 2. I'm crossing out, put your finger over this one, and I assume that I conclude that the dog does not bite, but it actually does. So practice with that, covering it with your finger. Type 1, covering up the first one. Type 2, covering up the second one. So type 1, I'm covering up that first one. I conclude that the dog bites. But it doesn't. And the result, let's say in this case, if I assume that the dog bites, I don't pet the dog, would be one result that could have happened. I don't pet the dog, but I don't get bit. So that seems kind of a safe way to go. Let's do the type 2 error. So 1, 2, I'm crossing out with my finger, I'm holding this over. I assume that the dog does not bite. So I conclude for myself that the dog doesn't bite. But it actually does. Result? Well, I concluded that the dog doesn't bite, so I did pet the dog. I was wrong. The dog does bite, and so I got bit. And so in this case, a type 2 error was a worse result. It's better to be cautious and not get bit, but I didn't get to pet the dog, whereas this one, I concluded I was wrong, and I got bit over it. Let's try another one. So number 5, given the null that it doesn't rain, H1, the alternative, I say that it does rain. So write a conclusion that result from a type 1 error. So type 1, with my finger, don't cross it out literally on your paper. I cross this out, I hold the finger over it. What did I assume? I conclude that it rains, but it actually doesn't rain. So I conclude that it rains, but it doesn't. So what is a result that could happen from that? If I said that it was going to rain, I said it's going to rain today. I bring my umbrella. But it doesn't rain. So it doesn't rain, so I didn't need it. Type 2 error. So I type 1, type 2, so I'm holding my finger over this. I concluded that it doesn't rain, but it did rain. So for type 2 error, I would have concluded that it doesn't rain, but it does. What's a conclusion or what's a result from that? Well, I said to myself that it's not going to rain, so I didn't bring my umbrella. But it does rain. I had already said that it wasn't going to rain, so I didn't bring my umbrella, and I got wet. So depending on the type, what your null alternative, let's say these were switched, type 1, type 2 might be a more serious error. So I could have you on a test question analyze both type 1, type 2 and see which one's the more severe one. And depending on how the alternative and the null were written, could be worse for the type 1, could be worse for the type 2.